We're now on video 2 about exothermic and endothermic reactions. In this one, we're going to explain why exothermic reactions give out energy and why endothermic reactions take in energy. If you're a little bit unsure about what an exothermic and endothermic reaction is, then watching the first video before this is probably sensible. Okay, so just a very, very quick recap. And exothermic reactions, temperature surrounding them goes up because they give out energy. Okay, in endothermic reactions, the temperature drops of the surroundings because they take in heat energy from the surroundings. Okay, so now we need to explain that. To explain that, you have to know this. You have to know that in any chemical reaction, whether it's exothermic or endothermic, in any chemical reaction, there's always two stages. The first stage is the reactants bonds need to break, and then when we've broken all the reactants bonds, then the product bonds need to be made, new bonds need to be made. So here we have got, for example, an equation for methane reacting with oxygen to make a carbon dioxide and water, standard gas burning, so gas in a Bunsen burner. Burning, that's what this reaction is. So here's our methane molecule. It's a carbon bonded to 4 hydrogen atoms. There's our oxygen molecules. So the methane is going to react with 2 oxygen molecules. So I've got 2 oxygen molecules here. Okay, so the first thing that has to happen in that reaction is we have to break these carbon-hydrogen bonds, and we have to break these oxygen-oxygen bonds. So the bond type to start with, a carbon-hydrogen. It's a carbon-hydrogen single bond. It's a single covalent bond like that. And there's 1, 2, 3, 4 of them. So we have to break 4 carbon-hydrogen bonds. Okay, oxygen is an oxygen-oxygen double bond. We've got a double covalent bond. There's 2 shared pairs in the overlap between the oxygen atoms there. And we've got, we don't have 4 bonds because a double bond isn't twice as strong as a single. It's about 1.5 times as strong. We have 2 oxygen-oxygen double bonds. So the bond type is an oxygen-oxygen double bond. It looks like equals, doesn't it? But it's not, it's a double bond. And there are 2 of them. 1, 2. So once we've done that, we've broken all these bonds. We've got all these atoms on their own. So the first stage is bond breaking. Bond breaking. That's the first stage. And the next stage, bond making. So once we've got all these atoms on their own, we need to make new bonds. We've got a carbon double bond oxygen there. So carbon double bond oxygen. We've got 1, 2 of them. 2 of them. We've got a hydrogen oxygen bond. 1 of them, 2 of them, 3 of them, 4 of them. Okay. And so we've got an oxygen hydrogen bond, 4 of them. Okay, so we need to understand that. Now bond breaking, if I'm going to take this pen and break it in half, I've got to put energy in to do that. Okay, so bonds breaking means energy needs to go in. Okay, energy in. Bond making. Now, if I had, think about this, if I had 2 magnets here, okay, one with a north pole there and a south pole there, not touching, and I let go of them, they would snap together. Okay, so that's energy going in, because that's what happens to these. That hydrogen snaps onto an oxygen, giving energy out. Okay, energy out. So making bonds gives energy out, and that's the same in all reactions. Energy in to start with, and then energy out afterwards. Now back to this Bunsen burner. If you think about that just for 1 second, okay? You turn the gas on in the Bunsen burner. What's the first thing you have to do? You have to hold a lit splint or a match to it. In other words, you have to put energy into that gas and that oxygen to get it reacting. After that happens, after that gas is lit, then lots of energy is given out when these new bonds are made. So when you put the energy in, when you put the match or the splint in, you're breaking these bonds to get to this stage. And then when all these rearrange and snap back together, they give out loads of energy, and that's the fire you see. Okay, so that's that. Now, and we've got this here. Chemical bonds are a little bit like magnets. They're not magnets, just it helps you think maybe. If you had 2 magnets stuck to each other and you had to break them apart, would you do this by putting energy in or energy coming out? Well, you'd put energy in to pull them apart. Put energy in. Likewise, when the magnets are separated but still close enough to attract, you decide to let them go and they snap back together. When the magnets are let go and are accelerating towards each other, does the movement require energy to put in, or is it given out? Answer is given out. Okay, so breaking bonds, energy in, making bonds, energy out. That's what you need to remember. Okay, so once we know that, we can start to put these things on a graph. Okay, we've got, this is called an energy level graph. What we have is we have two axes, energy on this axis and reaction path here. So this is like reactants on this side and products on this side. So we've got our energy level diagram here, which is a graph, and reactants on there, products there. This is the energy level, and you may say, why is methane up here and why is carbon dioxide and water down there? Well, think about it. Okay, gas has a lot of energy stored in it. You know that because if you put gas in a balloon and lit it, it would blow up. Okay, so the gas has energy stored in it. So gas and air mixed together has a lot of energy stored in it. Carbon dioxide and water, well, these are both used in fire extinguishers to put fire out. Okay, so there's really very, very little energy stored in these molecules, and so they're much lower down the graph. Okay, and when we burn the gas, these are our reactants and these are our products. So we've got to get from here to here. Now, but the first thing, remember, what happens is we have to put energy in. So when we light the methane, does our graph go upwards or does it go downwards? Well, we're putting a match in it. We're increasing the energy, so it's got to go up. It's got to go up. So we can label that energy in. Okay, so, and this is the same in every single reaction, because every single reaction we break bonds to start with. Break bonds. Okay? And then after we've put that energy in, we've got all those atoms on their own, and we've got to make these new bonds, and that gives energy out. So energy is given out, it's surroundings, so it's going to come down like this to this level here. Okay, so that's now going to be energy out. And hopefully you can see in this reaction, far more energy is given out than was needed to break the initial bonds. Energy out. Bond making. That's crucial, you know that. Okay? And it's this gap here that is the how much energy is given out in the entire reaction. That's the net energy transfer. Net energy transfer. Okay? Now the fact this is going downwards tells us that's exothermic. Because in an exothermic reaction, energy exits. More energy is exiting than was needed to break those initial bonds. Break those initial bonds there. Not very much energy was needed to do that. Okay, so this is a standard energy level diagram for an exothermic reaction. Okay, one other thing we can label, this gap from here to here, the amount of energy needed to start the reaction, because if you don't have that much energy, you can't start the reaction. We call that the activation energy. Activation energy. Activation energy on exothermic reactions isn't always that high. Okay, now, it says down here, sketch out a fully labelled energy level diagram for a thermal decomposition of calcium carbonate. This is an endothermic reaction. When the calcium carbonate decomposes, it forms calcium oxide and carbon dioxide. So we need the same graph, energy, reaction path. Let's label that up. Reaction path. Okay, on this graph we have reactants over here and products over here. All energy level diagrams are pretty much the same. On this axis we have energy. Now this time, this is an endothermic process. So calcium carbonate is a very common rock in the United Kingdom. It forms about a third of the rocks in the United Kingdom. It's used for building blocks and statues and things like that. It really has very little energy stored in it. So we'll put the calcium carbonate down here, CaCO3. There is our reactant. It has very little energy stored in it. Now if you heat calcium carbonate up, it breaks apart. It thermally decomposes it. You heat it, it breaks down. Thermal decomposition. Okay, the products of that are going to have a lot of energy stored in them. Calcium oxide. Calcium oxide. This used to be called quicklime in the old days because it starts with limestone. Calcium carbonate is limestone, and then you heat it and it breaks down to this calcium oxide, which is called quicklime. Quick is Old English for alive. In other words, it was limestone that had become alive because it has so much more energy stored in it. And carbon dioxide. Okay, calcium oxide and carbon dioxide. Most of the energy stored in the calcium oxide, of course. All right, so we have our reactants down here, we have our products up here because we had to put heat in to get there. Now, what's the first thing that happens in any chemical reaction? Bond breaking. Okay, so the first thing that has to happen is we have to break all the bonds in those calcium, carbon, and oxygen. That's going to take a great deal of energy. Okay, so that's energy in to break those bonds. So the energy level graph goes up. Energy in, bond breaking, bond breaking. So at the top here, I've now got calcium, carbon, and oxygen, oxygen, and oxygen, all on their own. Okay, so we've broken all the bonds that were holding them together in calcium carbonate. Next stage of any reaction after bond breaking is bond making. Now, making these new bonds doesn't give out very much energy in this case. So this down here now is bond making. Energy is given out, but not very much. Bond making, that's energy out. So in this reaction, the net energy transfer is a positive one. Okay, positive net energy transfer. Okay, the overall energy transfer from that place, which is the energy level of the reactants, to that place, the energy level of the products. Positive net energy transfer. The fact it's positive tells us it is endothermic. Okay, in this last example, the energy transfer was negative. A negative net energy transfer means it's exothermic. Compare and contrast these, okay? Both the same. Breaking bonds to start with, Ng to start with. So the Ng increases to start with in both reactions. Okay. After that, there's Ng given out. Okay. In the bond making. Bond making comes second in both reactions. Okay. The only difference is in exothermic, bond breaking is small and bond making is large. In endothermic, bond breaking is large and bond making is small. That is the end of that video explaining why reactions are exothermic and endothermic. What we're going to do in the next exothermic endothermic videos, we're going to look at putting a number to the overall exothermic or endothermic nature of the reaction by doing some bond energy calculations. That's the next video.